Hi guys, welcome to the second lecture in the unit on the Introduction to Biology. Today we're going to talk about the scientific method. You know, when I was your age, I didn't learn about the scientific method. I learned about the empirical method. So empiricism, empire, and the scientific method are the same thing. They're the same thing, and they're based on approaching the world, the phenomenal world, the thing you can observe, and by making measurements, and then by analyzing those measurements and drawing conclusions. Right. So that's the empirical method, and we alluded to the fact that this type of scientific thought started, at least 10,000 years ago, with recorded history, and there's thousands, millions of scientists furiously working away to expand what we know, what we really know, what we can back up with facts. Okay, so today, what's factual and what isn't has become a question of debate. But there exist facts, and empiricism and the scientific method is all about working to expose the truth at any cost, right? And so we use some steps. Now this is a misnomer. There isn't a scientific method, but I'm going to teach you 6 steps of the scientific method. And then the truth is, no science really goes in a stepwise fashion. It's all circular. You are constantly making changes and reevaluating your opinions. In fact, one of the most important things about science is that you have to start off understanding that you have implicit bias, right? That you're going to make mistakes just because of the experiences you have and the opinions you hold, all right? So we're all prejudiced. We all have experiences that inform how we make decisions. And the goal of every good scientist is to try to eliminate that subjective aspects of your experience and try to look at just the cold, hard facts. Just cold, hard facts, right? That's all we're interested in. So, so we observe and measure, and when in this course, I'm going to ask you guys to use mnemonic devices. Mnemonic devices, and mnemonic devices are ways to memorize things. Okay, a lot of the biology course is going to be the memorization of vocabulary terms, and it's not a super hard thing to do, but when it comes to large volumes of information, it takes some time. So anyway, the mnemonic device. The simplest mnemonic is something called an anagram, right? So an anagram is something like the FBI, right? So FBI stands for the Federal Bureau of Investigation. In this case, for the scientific method, the 6 steps, I want you to use the mnemonic O head case. And you got to be a head case to be a scientist. Look at this guy. O head case, it's OHEDCS, right? And those letters stand for the first step to make an observation, the second step to form a hypothesis, the third step to test the hypothesis with an experiment. We collect data with a D, we form conclusions, and then last but not least, all scientists want to share their work with their peers, right, with other scientists. Let's look at it in some detail. You know, New Jersey is also known as the Garden State, and that's because of its huge agricultural centers. And if you head down to the Jersey Shore, one of the things you're going to do before you get there is to drive through South Jersey. And if you're not on the highway, you get to see a lot of farmland. The soil there in South Jersey is really productive. One of the cool places in South Jersey is Johnson Sod Farm. And this isn't a picture of Farmer Johnson. Actually, there's a couple brothers, the Johnson brothers. But the sod farm is amazing. It's like 1,000 acres of like beautiful rolling Kentucky bluegrass, and that's all perfect. And of course, if you're a landscaper, that's where you get your sod from Johnson's farm. And so let's use this hypothetical Farmer Johnson, right? He's out in his sod, his grass fields, and he notices that when it rains, his grass gets greener. Right? So his first step of the scientific method is to observe a phenomenon and then pose a question. Right? So he sees the more it rains, the greener the grass is. The question is, what's the relationship between grass greenness and water? Notice he's only asking about the relationship between 2 things, 2 variables. Right? Because if he said, what's the relationship between soil, pH, and grass greenness, the amount of sunlight, and water, it gets too complicated, and you can't really do a good experiment with a bunch of different variables. We'll talk about that in a second. All right. So, what's the relationship between grass greenness and water? And next step is to formulate a hypothesis. Remember, a hypothesis is a prediction. It's an answer to your question. And Farmer Johnson says, well, I think the relationship between grass greenness and water is. Of course, all scientists are doing this with other variables. What's the relationship between X and Y? The simplest answers are seen in these graphs. Is there a direct relationship? Is there an indirect relationship? Yeah, these are graphs of a direct and indirect relationship. Hopefully you've heard of these terms before. Which graph is the direct relationship and which one is the indirect relationship? I'll give you a hint. Direct relationships have a positive slope. That's right, the graph on top is a direct relationship, and in a direct relationship, X and Y increase. They increase. As X increases, Y increases. In the indirect relationship, at the bottom, you have a negative slope as X increases, Y decreases, and vice versa. All right, and of course, we're talking about these linear relationships where Y equals mx plus b, and m is the slope. So Johnson thinks the more water you get, the greener the grass is going to be. So what does he do? Well, he tests his hypothesis. Now we test our hypothesis with an experiment. And a well-designed experiment has a lot of clearly defined parameters. We're going to call them controls. So for instance, Farmer Johnson comes up with an experiment where he takes 4 plots of grass, all 1 meter square. That's a control. Every plot of grass gets the same amount of sunlight every day. That's a control. The soil of each plot is exactly identical. The pH of the soil is exactly identical. That's a control. The type of grass is identical. That's a control. Now, what he wants to do to those plots of grass is to perform an experiment. In this case, he's really doing like 3 or 4 experiments. But to each plot of grass, he's going to get a slightly different amount of water each day or each week, and then see what happens. Now, he varies that one control, and we call that the controlled variable. Right? He controls that variable. Right? He changes that variable. Now, it depends on where you're hearing this. Sometimes that's also called the independent variable, which never made any sense to me. Right? A controlled variable is the thing you change. That makes sense. Independent? I don't understand. On the other hand, remember, the experiment's all about testing the effects of water. And so as he changes water, what he expects to see are changes in grass greenness. All right? And that's the thing that responds to the controlled variable, right? It's the dependent variable. It's also called the uncontrolled variable. So you've got to figure out a way to get this language straight, right? The controlled variable is the thing you change. The dependent variable is the thing that changes in response. It's controlled, independent, uncontrolled, dependent. If you notice that the 2 pairs of words that mean the same thing either have a prefix or not, maybe that'll help you remember this, but that's it. All right. So to make it even further complicated with this word control, you have experimental setups where you're actually doing the experiment. Then you always have a control setup. So what is the control setup? Well, the control setup is the experimental setup minus the controlled variable. So he has this 4th plot. It's identical to the other 4 plots, except he doesn't give it any water. That's the controlled setup, right? It doesn't get the controlled variable. And the purpose of the controlled setup is to establish causality, okay? You can relate all kinds of different phenomena. For instance, you could find out that people who are taller have higher IQ. Now, there's no truth to that. But you wouldn't expect that your height really had anything to do with your IQ, right? So you can have a relationship that doesn't have causality. And that's the purpose of the control setup, okay? And we'll look at that in some detail in the activity I've designed for you guys to do. Now, experiments lead to other experiments. But before you do your experiment, guess what? You should do some research, because there's a really good chance that one of the millions of other scientists or farmers have done this experiment already, and you can find out exactly what you want to know. And of course, those whatever experiments you do or they've done might lead to new experiments, right? We'll expand that scientific knowledge. Of course, when you're doing your experiments, one of the things you got to do is collect your data. And we use mathematical instruments to collect and analyze data, right? Of course, one of the things you're going to do is write it down into a table. And here's Farmer Johnson's table where he has these different plots of grass, and he gives them different amounts of water over time. And then he can plot them in a graph to see what happens. So here's the different, plot 1 through 4. And you can look at that and make or interpret the graphs. Okay, one of the great things about mathematical analysis is that it can help you identify bias. Kids will always say, like, Mr. Doherty, why are we doing math in science class? Well, the answer is because science is math. All science, all good science, all real science comes down to a mathematical analysis, all right? And mathematical analysis allow you to draw accurate conclusions, all right? Draw tell whether or not the data you've collected actually shows relationship or doesn't. We use graphs all the time. Here's some important graphs for kids in the 21st century. This is the world's temperature over the past, 4 billion years. Back in the day, it was really hot here. Why? Well, it was like a ball of molten gas and lava. And temperatures have dropped. We're down here. I've blown that little section up, and you can see that over the past 500,000 years, 500,000 years, temperature's gone up and down and up and down and up and down and up and down. So that's the red is the temperature graph, and we're going up. And you can see that there's also a graph of CO2 concentrations, and that's important. Like, why are we worried about CO2 concentrations? Well, you can see there's a high correlation between CO2 levels and global temperatures. And of course, this graph is a little bit old because guess what's happened to the CO2 levels? They're all the way up here now. And we've blown past this 500,000 year maximum. Here's another cool graph. Wow, look, United States, we're ahead. Oh, that's not a good thing. This is the COVID graph, right? I'm recording this June 18th, so I don't know what's going to happen by the time you guys see this, but I can imagine this is going to continue to rise. Yeah. Anyway. So I collect data, I analyze the data using mathematical instruments like, averages and means and median modes. And I can do other kinds of statistical interpretations, right? Like look for standard deviations or percent error, which allows me to finally draw a conclusion, right? So a conclusion really just says, does the data I've collected support my hypothesis? Or it doesn't support my hypothesis. Is there a relationship between X and Y? And so conclusions are very concise, right? Very simple. And that's it. And hopefully, your conclusion supports your hypothesis. And hopefully, you can be the primary author of some peer-reviewed journal article, because the final step in the scientific method is to share your work, all right? And you share your work through this scientific research community, all right? So for every you would do peer-reviewed consensus, which means that you would publish your work to an article, and it would be reviewed by other experts in the field in the universities or in the private sector, and they would look at the data you've collected and look at your experiment and say, like, well, look, is this a valid experiment? Is this data look good and sound, and are the conclusions that you've drawn from your data reasonable? And of course, if you're lucky, you get to have your material published as part of the growing body of scientific evidence, all right? Remember, the goal of science is to approach the world from an objective standpoint, look at the phenomenal world and measure it and analyze it and understand it in hopes of uncovering the truth, right? And, one of the truths is we're all humans. There are no real boulders there. And of course, we want to share data with everybody around the world because there's a good chance we can all live a nice, happy life here on planet Earth if we recognize our biases and work to eliminate them. That's it for the scientific method, and I've got a little activity designed to follow this up. Thank you.